Hello, everyone. One of the videos we made was measurement and uncertainty. Then we made another one on significant digits and when they fail. Now I'm going to do a video on scientific notation followed by dimensional analysis. So this is normally, these three videos should comprise the beginning chapter of any algebra-based or calculus-based physics, as well as introductory chemistry and stuff like that. So hopefully it'll be of some help. So I'm going to start off by talking about scientific notation. We've already alluded to it in a couple of the other videos about how you can deal with significant digits or significant figures a little more straightforwardly and less ambiguously by using scientific notation. So now I'm going to show you some other advantages and disadvantages. So I'm going to start by showing you my other camera. So in physics, we encounter very big and very small numbers. And one of the main advantages to dealing with scientific notation is you can make very big and very small numbers take up a lot less paper and make them less prone to error. So one such example is, for instance, the gravitational constant. And by all means, this is nowhere near one of the smallest, but it is a very small number. G is the symbol it's given. It's I'm going to write it out in nastiness, all its nastiness. And I'm only going to use really 3 sig figs. So it's 0.0000000. Notice how I keep them in pods of 3 when I'm writing out a decimal. That's a good thing to do when you're dealing with your instructors as well, because we're not technically supposed to use commas. I would even accept commas in my class, but the main thing is if you do them by pods of 3, it makes it a lot easier for us to see. So that's 9, 10, 6, 6, 7, and the units for that are Newton meters squared per kilogram squared. So that's a typical small number, if you will, that we'll encounter in physics. Now, the idea with significant digits, or excuse me, with scientific notation, is that we want to write this number as a number between 1 and 10. So I want a number, and it's got to be less than 10, but greater than or equal to 1. And that number would then be multiplied by 10 to some power. Okay. Now, in order for us to really make sense of that, what you got to realize is if I have 364 times 10, you just add a 0 on the end, which is sort of like taking the decimal place, which is understood to be here, and moving it one place to the right. If I did 364 times 10,000, I would just add 4 zeros on the end. And of course, it'd be helpful to put commas here. Remember, when you do your commas, you technically go from the right-hand side. Okay, so in that case, notice it's done the same thing as, since the decimal is understood to be here, I basically moved the decimal 4 places to the right. So another thing that might be helpful is realizing that 10 times 10, which is called 10 squared, is 100. Notice the exponent matches a number of zeros. 10 times 10 times 10 times 10 is 10 to the 4th. And that, of course, is 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. Again, the exponent matches the number of zeros. So if you wish to move the decimal to the right, you just multiply by powers of 10. In this case, I would like to move this decimal, remember it's got to be between 1 and 10, so I move it there. That wouldn't be it, that's way too small. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's still less than 1, so that's not good. If I went all the way over to here, that's 66. That's bigger than 1. So I have to go right here. That's between 1 and 10. So I actually have to move the decimal 11 places to the right. Okay. So to do that, I'd really have to multiply this by 10 to the 11th. But in order to multiply by 10 to the 11th, you've already changed the value. So I have to do the opposite, which is divide by 10 to the 11th. And if you take and do, let's say, G divided by 10 to the 11th, that's the same thing as G. I was ugly G I drew first round. As G times 1 over 10 to the 11th, which if you remember your exponent rules, that's the same thing as 10 to the negative 11th. So in order for me to put this number in scientific notation, in order to get it into the number between 1 and 10, I had to multiply it by 10 to the 11th to get it over here. And if I multiply a number by 10 to the 11th, I've changed its value. So I also have to divide by 10 to the 11th. So I'm essentially just multiplying by 1, right? So I'm multiplying by 10 to the 11th to make this small enough, or excuse me, big enough in this case. And then I'm dividing by 10 to the 11th to correct for that. So ultimately, what I'd say is G is that number, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So that's how you could do, for instance, a very small number. We also encounter very big numbers in science, and one of those, for instance, and not really the biggest, but it's at least the biggest speed, and that's c, the speed of light, which is 299,792,458 meters per second. And again, you can put commas here if you wish. Okay. So in this case, I want the number to be between 1 and 10 because that's our rule with scientific notation. So the decimal is understood to be here. In this case, I got to move the decimal to the left. Well, if you did, let's say 42,000, let's do 42 million. What the heck? Divided by 10, I think you know that that is 420,000. In other words, I'm making it one digit smaller. 0,0,0,0. 1, 2, 3, 4, 5, 6. 1, 2, 3. Up, too many zeros. Okay. So now I can put my comma. That's what threw me off. I was trying to put my comma somewhere. So now I'll have to put my comma over here. And what's happened is I divided by 10. That made me move the decimal one place to the left. In fact, if I divide by 10 to the 2, I'm going to move it 2 places to the left. 10 to the 3, 3 places to the left. 10 to the 4, 4 places to the left. So in order for me to make this number in the proper, they call it a mantissa, the proper mantissa form, that's this number. If I want to make it into a mantissa that's proper, I can't move the decimal 1 place because that's still way too big. 2, 3, 4, 5, 6, 7. 7's not enough either. I'm at 299. 1, 2, 3, 4, 6, 7, and then at 29, excuse me. So 1, 2, 3, 4, 5, 6. 7's not big enough. I'm at 29.9. 8 is 2.9. That is between 1 and 10. So I have to put the decimal right there. So I now can say C will equal 2.99792,458. Now I've got a number between 1 and 10. But in doing so, I divided by 10 to the 8th. But if you divide by 10 to the 8th, you also have to multiply by 10 to the 8th so that you're doing the equivalent of multiplying by 1. So I've already divided by 10 to the 8th. Now I need to multiply by 10 to the 8th. So I'll say times 10 to the 8th meters per second. And really, we usually don't use this many digits. And in fact, this actually made the number longer to write by putting it in scientific notation. But I wanted to show you all the digits just for Just so you know, scientifically, we actually have that many digits. In fact, it's defined now. The speed of light is now defined, actually defines the unit of length such that the unit of length is a meter. The base unit is the amount of time, or is the distance light travels in 1 second. So it's, or excuse me, 1 over 299,792,458 of a second. Okay. So that's how you actually convert a big number to scientific notation, and a small number up here to scientific notation. Notice a big number, a number that's much, much, much greater than 1, ends up getting a positive exponent. And a small number gets a negative exponent. So this number was very, very small. So it got basically 10 to the negative 11th. And this number was very big, so it got an exponent of 10 to the 8th, which is a positive. Okay, so that's the rule of thumb. Now, how do you go the other way? What about if I gave you a number that's in scientific notation and I asked you to write it in decimal form? Well, that's easy peasy. One such number is E, the magnitude of the charge of the electron, which is 1.602 times 10 to the negative 19th coulombs. So this is actually the prescription. It's telling you exactly what to do. It's saying, hey, here's 10 to the 19th being divided, because there's a negative there, being divided into this. And when you divide a number by 10 to the 19th, that means you got to move the decimal 19 places to the left. So I get 0.123456789 10 11 12 13 14 15 16 17 18, and then if I go one more place, that'd be 19, so it's 1602. So notice it has, if I wanted to make this in scientific notation, I have to move the decimal to the right. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19, which is what I expected, places to the right, which means I had to multiply it by 10 to the positive 19. But if I got to do that, I also got to divide it by 10 to the negative, by 10 to the 19th, and that's why the thing was negative. So that's the actual result of converting it to standard form from scientific notation. In another case, let's say Avogadro's number. Avogadro's number is Na is equal to 6.022 times 10 to the 23rd. That's going to be even worse, only this one, notice they're multiplying times 10 to the 23rd, so that means move this decimal 23 places to the right. So I'll say 6, 2, 2, that's one place, two place, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And I grouped them all together because I wasn't really sure exactly how many places I was going to be able to put in the commas. So now I go back from the other side and I can put in the commas, each 3. So Avogadro's number, and it has units, by the way, of reciprocal moles. That's 1 over moles, or per mole. Okay, so you see now that 6.022, whoa, nelly. I left off the O. I did 6.0, I just did 622. So that should start off at 3, which means all my commas are off and should be one more place over there, because this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So yeah, all those commas are off. I'm going to correct it now. It's going to be 6022. And now I'm going to start, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. reciprocal moles. This is a big X where I made a boo-boo there. And now you can go back and put our commas in 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. There you go. So that is Avogadro's number in standard notation as opposed to scientific notation. So that's basically it. You just have to know how to put numbers in scientific notation from standard notation and how to put numbers in standard notation from scientific notation. And we've done with that part. So now I'll ask you guys to consider something called dimensional analysis. Now, this is a really powerful thing. It allows us to check whether our units are right. Remember, for instance, two numbers can't be added unless they have the same units or no units at all. Numbers with units, by the way, are called denominate numbers, D-E-N-O-M-I-N-A-T-E, like denomination. So they're denominate numbers, and you can only add and subtract numbers with exactly the same units if they're denominate numbers or pure numbers, whereas you can multiply and divide numbers all day long with different units. Okay, but in doing that, some things have to be true. So if you're writing out an equals, the units on the left have to equal the units on the right and stuff like that. So let me give you a typical example. If you look at your speedometer on your car, you'll notice that it reads miles per hour or kilometers per hour. That is a distance divided by a time, and we normally would say that velocity is equal to the change in distance, which is registered or measured by x, divided by the change in time. That's another thing. That delta is the uppercase Greek letter delta, which is just a triangle. That means change in. That's so in physics and chemistry and virtually every science. And it's understood to mean final value of, say, x minus initial value of x. Okay, so whenever you see a delta, that's in all your science classes, that should mean change in. So in this case, the velocity based on our speedometer should be change in position over change in time, or distance divided by time. So what I say is dimensionally, and I put square brackets around it, that means I'm not caring about the numbers, I'm just caring about the units. Dimension should be equal to the unit length over the unit time. So remember, we're dealing with, according to the SI system, we're dealing with the MKS system, which means meters, kilograms, seconds. So that means our unit of mass in dimensional analysis, we're just going to use, it's kind of weird because this is supposed to be meters, kilograms, and seconds. But anyways, we use length for meters, and we use M for mass, and we use seconds for time. Actually, excuse me, we use T for time. So using that, now I know what velocity should be. Well, what if I told you that the velocity on a string is supposed to be used to the mass, is supposed to be related to the mass per unit length. So V on a string is related to the mu, which is mass. So I'm going to say mass per unit length, and the tension in a string. Okay, that's the two parameters that I'm hypothesizing velocity is on a string is related to. So imagine a guitar string. If you take a guitar string and if you pull it tighter, it actually gets a higher pitch, which actually means that the frequency goes up, which causes is basically because the wavelength went down. So you can sort of think of that as a velocity of a string, a wave on a string. And that can start making you think, okay, well, yeah, the tension should matter. If you also look at the strings on a guitar, you'll see that the one that makes the highest pitch is the thinnest little string, so that probably has the smallest mass per unit length. So yeah, this seems kind of reasonable. But the thing is, we have to deal with a tension, which is really a force. So what I'm going to use is something else. I'm going to say, well, wait a second. I know that velocity is changing distance divided by change in time. So I know what units that should have. That should be L over T. That's the dimensions, okay? Now, what I have to figure out is this will be related to mu to some power, let's say the n power. And it's going to be related to the tension to some power, let's say the m power. So this is what we're going to work out and try to see if we can find out a formula possibly for the velocity of a wave on a string. So this is actually the dimensions of the velocity has to equal all that. So this gives me an equation. This part and this part gives me an equation. Once I know the dimensions of this, which I already gave you, and now this I got to figure out. Well, the one thing we know about force is that Newton's second law, which is one of the two equations everybody in the world has heard of, E equals mc squared being one, and the other one being F equals, yeah, you probably got it, F equals ma. Okay, so F clearly has units of, or dimensions of, mass times dimensions of acceleration. So what's acceleration? Well, if you talk to a car dealership about a car and they want to tell you how well it accelerates, they'll give you the 0 to 60 time. So a fast car, for instance, might go, or a car with a good deal of acceleration might go 0 to 60 in 4 seconds. So 0 to 60 miles per hour in 4 seconds. That's a pretty good acceleration. But what does it mean? Well, it means that my speed or velocity changed from 0 to 60 miles per hour in a certain amount of time. And that might make you think that maybe acceleration is equal to delta V over delta T. And that's exactly what it is. Okay. It's, well, at least that's the average. So the acceleration is supposed to be velocity over time. So with that, we can say that the acceleration dimensions are length per time divided by time, which is, working out the math, length per time squared. So we now have the dimensions of acceleration. So now I can say the dimensions of force are ml over t squared. So now I know the dimensions of tension. So now I have L over T for the velocity is equal to m over L raised to the n power times the tension raised to the m power. And the tension, of course, is a force, so that's length times, mass times length per time squared, mass times length per time squared, and that's going to be raised to the lowercase m power. So I got L to the 1, t to the minus 1, notice that's the same thing as t being in the bottom, is equal to, here I have an m to the n power and an m to the m power, so this is m to the n plus m power for just the m's. So I've taken care of those two guys. Now I have an L to the negative n power and an L to the m power. So that's going to be L to the m minus L power. So now I've taken care of these two. And then finally, I have a t to the negative 2m power. And I've taken care of this one. Okay. Well, I see no m's over there, so that gives me one equation. N plus m must be equal to 0, because that's the only way we're going to make this m disappear. Right? I do see a L over here, and that's 1, so that gives me another equation, and that is m minus L is equal to 1. And then I see t is actually raised to the negative 1 power, so that gives me yet another equation. Negative 2m is equal to negative 1. So from that, I can get that m must equal 1/2. right? If I divide both sides by -2, -1 over -2 is just going to be 1/2. So I got m is 1/2. Now I can plug that in. So n plus 1/2 equals 0. That's from the top equation. Gives me that, in fact, n must equal -1/2. Okay, so now I got both powers. And just to make sure that works, we have to do m minus L and figure out exactly, you know, where did m minus L go? That's not n minus L. It's m minus n, duh. I copied that wrong. So now that makes sense. M minus m, since m and m are opposite, n and m are opposite in sign, m minus n is clearly true. So all three of these are satisfied. So what do we get from that? We see that the velocity of a wave on a string is equal to mu to the n power, which is in n is -1/2. So I have to put mu down here, and t to the m power, which is +1/2. So I'll put m up there, but they're to the square root. And lo and behold, if you look in your textbook on the chapters on waves and strings, you will find that that is exactly the expression for the velocity of a wave on a string. That's the power of dimensional analysis. Now, the thing is, if we came up with that as a hypothesis and we did an experiment, that could be off by a factor of 2 million, because it might actually have a pure number of 2 million in front. We don't normally find that, but occasionally we'll find things like pi and 2 pi and stuff like that on it. So that is something you got to keep in mind. This only gives you an equation up to a multiplicative constant. That long as that multiplier is a unitless number or dimensionless number, then you still have a correct answer. So, or at least an answer that agrees with what you worked out. Another example of this would be the period of a pendulum. So the period of the pendulum is really the time it takes for the pendulum to swing and all the way back. That's the period, so it's a time. Period t of a pendulum. It turns out it's kind of neat. The period of the pendulum depends on the length of the pendulum and the gravitational acceleration. So, and that's it. It doesn't depend on the mass at all. So that's kind of an interesting thing, and it's a way you can actually use to determine the gravitational acceleration on a given planet. So let's try this dimensional analysis and see if we can work out a formula for the period of the pendulum. So the period of the pendulum t has dimensions just plain t. Okay. The obviously the length has dimensions of just length, and gravitational acceleration is an acceleration. So the dimensions of gravitational acceleration is just L over t squared, like we worked out here. So let's say t, the period of the pendulum, there's the unit, is equal to L to the m times g to the n. If that's the case, of course, this is dimension g and dimension L. If that's the case, then I have t is equal to L to the m, because the units for length or the dimensions for length are just L. But then in this case, I have L over t squared for n, raised to the n power. So now I have, writing this another way, t to the 1 power is equal to L to the m power. Now the L is also raised to the n power, so it'd be m plus n. And the t to the 2 is actually t to the -2 raised to the n power, so that's t to the -2n. So t to the -2n. That's basically it. That's the only thing we have. So we know t has a power of 1, so -2n. T has a power of 1, so we know -2n must be equal to 1. So that tells us that n is equal to -1/2. We also know that there's no L over here, so m plus n must equal 0. So given that n is negative 1/2, m must be plus 1/2. So ultimately, our formula for the period of a pendulum is the square root of the m was the positive 1/2, and that was the power we put the L to. So it's the length of the pendulum, which I'll write as script L, over gravitational acceleration, all under the square root, again, because exponent of 1/2 means square root. So there's another formula we could derive just from dimensional analysis. So that's sort of the power of this. You could also use, instead of using dimensions, these abstract L, M, and T's, you can also use meters, kilograms, and seconds, and that's fine, except at that point you're actually doing unit analysis as opposed to dimensional analysis, but it's still the same thing. So hopefully that'll be enough to help you figure out how to do dimensional analysis stuff. There's a really cool one if you want to look up the units. You can derive something that's used in modern physics right now, and it's called the Planck length. And basically the Planck length depends on, well, for starters, it's a length. So it has a unit of or a dimension of L, but it depends on h bar, which is just h over 2 pi. So you can look up the units of h, and that'll work out fine. And it's also dependent on gravitational acceleration, g, which is what we introduced earlier, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And it's also related to c, the speed of light. So you can say L is equal to the dimensions of h bar to the n power, g to the m power, and c, the speed of light, to the L power, if you want. Okay, and work all that out, and you will actually get exactly the correct response for what the Planck length is, and then you can Google it and check it out if you want. Just for the record, h bar's dimensions are, I would say, length times mass. Oh, actually, let me write this a little clearer. Mass times length over time, and that ends up becoming mass squared. Yes, that's it. So that's the dimensions of Planck's constant, m squared L over t. We already told you about g, but I'll reiterate that is the units of force, which you can look above to find that. It's also the unit of the length squared over the unit of the mass squared. So that's g. And of course, c is just the speed of light. It's just a speed, so that's L over t. Try if you want to see something, and then look it up on the Google machine, and you will almost certainly get the right answer unless you made an algebraic mistake. So I hope that helps everyone. Have a good day.